Welcome everybody. Thank you for attending today's Westpak's webinar on combined environment testing. I'm Greg Swinghammer and I'll be your moderator and webinar organizer today. Today's presenters are Herb Schoeneman and Mike Brown. You may remember them from the last webinar on the introduction to reliability testing. Mike is a lab manager here at Westpak and has been with Westpak for 6 years and also has just completed his MBA from Santa Clara University. Herb is the president and CEO of Westpak and has been here since the beginning. Herb, take it away.
Well, thank you, Greg, and welcome everybody on this fine Thursday afternoon. Westpak as a company is about 27 years old, and we're dedicated to product improvement and safe product delivery through dynamic testing. That's our secret sauce. We test things. We break things occasionally. Several years ago, we instituted divisions within our company to focus on the particular market segments that we serve. One of these focus areas is product reliability. As Greg mentioned, last fall we presented an introductory webinar explaining some of the test procedures used in reliability testing of products and how some of the tests were run. Had an excellent response to that webinar, and we were asked to take it to the next level, specifically to investigate areas that would include 2 or more dynamic inputs delivered to the same product simultaneously. And that's the topic of today's session. So now I'm going to turn it over to Mike Brown, who will introduce the topic and lay out the groundwork. Mike?
Thank you, Herb. Thank you, Greg. So brief agenda of this afternoon's discussion. We'll have a brief kind of why and how of product reliability testing. We'll talk about defining your product's environment and what's unique about your product's environment. Most of the combined environment methodologies we'll discuss today only apply to some specialized product classes. We'll go over 6 or 7 combined environment methodologies, and we'll talk about the background of those tests, some of the common parameters and standards, industry standards where they're applicable, a little discussion about testing to level or testing to failure, and some typical results and findings, and we'll wrap it up with a summary and questions. We'll pause a couple times throughout for questions as they arise. So first off, why test? First we need to define what product reliability is. It's the ability of the product to meet its design criteria. The products will see many hazards throughout their lives. So some to think about are the indoor and outdoor storage and operating environments, rough handling and usage by the user, operating conditions, whatever those may be. So if you're operating on a truck or an aircraft or walking around, what have you. And then also the shipment and installation environments. And oftentimes for large capital equipment, this is the most severe an environment the product will ever see. There may be regulatory requirements to think about. Most of those are around efficacy and safety, not so much long-term reliability. And then lastly, and perhaps most importantly, think about customer satisfaction, low warranty claims, and low long-term liability for the use of your product. Herb?
Thanks, Mike. It's important to remember that an irreversibly negative company image can result from poor product reliability. Customer frustration and a variety of other negatives can result. I'm sure you can all recall segments of your history, where you had a problem with a product and it just drove you nuts. So making sure that the product is rugged and reliable makes extremely good business sense. The cost of a recall, a poor product image, and a variety of other factors can make the cost of testing very reasonable in comparison. In addition, repeat clients are the easiest, loyalist, and least expensive to get. So once you've got a good client, keep that good client with good product reliability. Okay, Mike?
All right, so some things to consider before doing any testing is focus around design and design for reliability. So some common things we see or best practices we would suggest would be first to reference existing solutions. If there's a similar product in your class, look at the way they may have addressed engineering problems or learned from prior industry knowledge and experience. Think about thermal expansion and contraction issues. Often when using your dissimilar materials, so say you have a part metal and part polymeric or plastic product, the plastic's going to expand and contract a lot more with temperature than the metal, and things will come apart over time. Think about material compatibility. So we see a lot of issues with dissimilar metals. with corrosion in humid and corrosive atmospheres like salt fog. Think about hardware backout, so think about having torque specs for everything, or using thread lock or nylock nuts. Oftentimes we see things coming apart in vibration or other mechanical inputs. And think about production process control. So with all these previously mentioned things, when you're actually building the units, most of the units we test are prototype units or early development units. So make sure everything hopefully has a torque spec and are being followed both in development and in your final process. We oftentimes see production units come through, and the issues they're having, these are their final units, have to do with production process control. Also think about, there may be regulatory requirements, there may be safety requirements, or there may be requirements about the function of the product. Usually these aren't really reliability requirements per se, but sometimes there is overlap. So a product may have to survive at extreme temperatures or something similar. Herb, would you like to add anything?
Thank you, Mike. When thinking about the product design for reliability, remember that new products are probably not really new at all. Most of them can be thought of as recombinations of existing materials or fabrications or processes put together in a different fashion or for a different reason or for different materials or different markets. Because of this, it's relatively easy, it's not that difficult, to leverage on previous history, including materials testing, processes, and a host of other factors. None other than Albert Einstein told us that it's been a long time since the world has witnessed a truly new and innovative idea. So remember, you can always leverage on what's been done in the past, at least to some extent. Mike?
Thank you. So let's talk a little bit about establishing the test plan, what you actually need to do. So we call this design of experiment, or DOE. And the starting point of this is characterizing the environments that your EUT or equipment under test will see throughout its lifespan. So what we're trying to do here is define test inputs to cover all of these anticipated environments. Once you've done that, you should consider combined environments, and that's going to be the focus of our technical discussion in a few minutes. So where you have something like temperature and vibration combined, or temperature and mechanical cycling combined, you may have unique failure modes or issues that only occur in those combined environments. And as mentioned before, keep in mind you have to ship or distribute your product, and this can be the most severe mechanical input the product will see depending on its end-use classification. Next is to determine the acceptance criteria or inspection criteria for your product. So where possible, be quantitative. So obviously function or not is a good thing. If you have things like mechanical insertion or removal forces or dimensionality requirements, those are all very good. And then also think about cosmetic things. So if it still works fine, but it's damaged or doesn't look good, and a consumer may have an issue with it, that's something to try and quantify and consider. And then also safety. If the product does have a failure or something goes wrong, it's posed a hazard to the end user. When you're doing all this, think about doing a test to level or test to failure. So what we mean by this is test to level would be the minimum requirement your product needs to survive through to be something you're willing to put your name on and sell, whereas test to failure would be continuing testing beyond that, either at a higher level of intensity or for longer duration, to see how the product will ultimately fail, and then hopefully learn from that and make improvements to your product from those learnings. And then lastly here, start small. One mistake we see sometimes, or misstep, people come in and want to test everything all at once on a brand new product. We generally don't recommend that. Start with basic temperature testing and basic mechanical vibration testing. See what happens, expect to have findings and to learn from them. And then go through comprehensive single environment testing. So test all these different test inputs one at a time. This first subject, Herb and I did a webinar on in November. It's available on the Westpak website. I encourage you to look at it. So third, in today's topic, is combined environment testing as applicable. So where you find unique combined environments your product may be exposed to, define those and test to those last. Herb?
Thanks, Mike. It's important to keep in mind that without a plan, nothing will ever happen. That's why this planning is important. Fortunately, there are aids such as design of experiments and similar that can help us tremendously in coming up with a plan for this reliability test. By using some of these rather simple and straightforward criteria, that plan can be made into something that will form the basis for starting your testing. Almost always, refinements are made in the plan as you move along based on what is witnessed during some of the initial tests. I don't think we've ever seen a test protocol completed on reliability testing exactly as it was initiated. There's always changes that you just want to make and should make during the test. Refinements are made as you move along based on what you see. This is normal and natural. It's not necessary to have every I dotted and T crossed as you move into the test. So a fully developed test plan is a starting point. It is necessary, however, to understand the goal of the testing and the endpoint that you are trying to reach. What is the goal that you're trying to reach? And it's always improved reliability, a better product, a more reliable product. So keep that in mind. Keep that as your focus. Okay, Mike?
Thank you, Herb. So that wraps up kind of our introduction. Are there any questions at this point, Greg?
Not really at this time. There's a couple comments, but let me see here. One just came in. How do you justify against management to do more testing instead of performing qualification testing? Does that make sense?
Not quite sure I understand that question. What I would say to justify why you should do product reliability testing in general is to hedge against long-term liability and warranty claims. And with that, if something breaks, and even if your company makes it right, you probably don't have the happiest customer. Anyway, maybe we can continue that question later in the webinar.
Okay, yeah, let's come back around to that.
Okay, well, thank you. So, moving on to kind of the core of our session today is the combined environmental test inputs we'll be discussing. So first off, for the sake of our discussion, our sample EUT is going to be a ruggedized laptop computer. So imagine a laptop that you can use in the rain, you can drop it in a puddle of water, you can drop it period, and it's built for that, rugged, beefy laptop. The test inputs we'll discuss today, there's a total of 7. The first will be temperature and vibration testing. This is called sometimes agree testing. The next will be impact testing at temperature extremes. And so by impact, we mean physical impact, so dropping a steel ball or hail impact or something similar to a product. The next is freefall drop testing at temperature extremes. So that's physically dropping a product from your hands or something similar to the ground. The next is mechanical cycling at temperature extremes. So this would be actuating buttons or hinges or switches at thermal extremes. The next is temperature and pressure. So this would be altitude or high pressure testing, submersion type testing. The next is fluid submersion with temperature and pressure. So you have a high level of depth, varying temperature. And the last is thermal shock by water spray. In general, having a warm product and rapidly cooling it with water spray. Herb, you have?
It's important to remember that combined environments testing, our subject today, grew out of the realization that temperature changes and vibration, among others, caused stress levels that were typically found in the environment yet rarely tested in the laboratory. Mil-spec testing was the first to incorporate this so-called shake and bake concept, and it grew quickly into what Mike mentioned before, AGREE. AGREE stands for Advisory Group on Reliability of Electronic Equipment. This is a group put together in the late 50s, actually, to help with military reliability testing. It's become a standard in the U.S. The primary difference between AGREE testing and shake and bake is that AGREE, at least as it currently exists, utilizes both temperature and humidity inputs along with vibration, whereas shake and bake is temperature and vibration only. There are many other examples of combined environments testing that make sense for a given product, a given environment, where specific materials are combined. Most of these combination tests are not covered by specific test protocols, the IECs or the ASTMs or things like that, because they tend to be unique in their application and usage, which is why we picked on them today. Often, levels specified for a single environment input are brought over into a combined environments test in order to simplify the process, at least the starting point. In general, however, combined environment tests are unique, and we're going to emphasize this as we move along. Mike?
Thank you. So as we go into this, if you've probably noticed, all of these tests have some sort of temperature or thermal component. That's going to make a big difference on how your materials react. So some kind of background on basic temperature testing. First off, we have a temperature humidity chamber pictured here. This is kind of a medium-sized one. We have our laptop in it. Some of the basic tests we'll run would be to simulate the storage environment, so just temperature and humidity extremes. The shipment environment, and that generally is 3 conditions. You'll have a cold condition, a frozen condition actually, a desert condition, so warm and dry, and then a tropical condition, warm and high humidity or wet. You can have the unit operating, so as you see it here, and you can look for things like the heat rejection off the unit, so how much heat it introduces into the environment. Cyclically turning the unit on and off to stress its thermal components, especially when the chamber's at a very cold condition. Imagine everything frozen, you get some internal heating in your circuits, that can cause issues. And then temperature rise. So if you have the unit operating in a very warm environment, can it convectively cool itself sufficiently? Another common thing we'll do is to vary the electrical input into the product. So imagine this thing has a universal power supply. It can take, say, 100 volts AC to 240 volts AC. How does it operate at those extreme conditions at varying temperatures? The test profiles themselves will either be static, where we go to a condition and stay there anywhere from a few hours to a few days. Cyclic, where you'll rapidly cycle between 2 extremes. The transition rates are generally 1-2 degrees C per minute, somewhere around there. And then lastly, what we call a thermal shock profile, where you very rapidly transition from one condition to the other. This is generally done with a chamber that has 2 compartments, if you would, one very hot, one very cold, and you mechanically transition a unit from one to the other. For all these stress tests, there's a concept called a 4-corner test. So let's take our temperature and voltage example. We would test high and low temperature and high or low voltage input into the unit and make sure it operates in all 4 of those conditions. And the idea here is that if it can operate at those 4 extremes, all the area contained within that box, it should do fine in. That concept applies to most of the tests we'll discuss today. There are many test standards that discuss temperature testing. Some of them are listed here, and there are many others. Common issues that we see with just temperature testing, as mentioned before, thermal expansion issues, exceeding material limits, especially with warm stuff. You have permanent deformation, plastics getting soft. With cold stuff, you may see brittle material, so if there's any movement, things can break unexpectedly, and just general mechanical failures.
Thanks, Mike. In reviewing the basic temperature testing, as well as the previous slide that showed the 7 combined environments that we're going to be talking about, the one common element we see is temperature. Temperature is the big killer. This phenomenon of temperature change in the environment is very common. It happens daily, cyclical, and this one important input will occur. I mean, it has 100% certainty. It's going to happen. So that's why it's very important to test for. It's also very destructive, potentially. And the reason is that most materials expand with rising temperatures and they'll contract with cooling temperatures. That's the nature of the beast. And sometimes this change is exaggerated, sometimes it's subtle. It's always stressful, primarily because when you have 2 different materials fastened together, they'll expand and contract at different rates. This is bound to produce stress sooner or later. Something's got to give. Some popular materials such as aluminum tend to have very high expansion and contraction rates with temperature than other common materials, and therefore stress is common with aluminum structures and components. Thermal problems are not limited to aluminum, however. Some polymers will actually change their characteristics depending on the temperature itself, typically when the high temperature exceeds their thermal melt index. So temperature is the killer. That's why we're focusing on it. It's a component of all the combined ones that we're going to be starting to talk about right now. Mike, want to start that process?
All right, so here's our first combined environment test. It's temperature and vibration, and this is often called agree testing. This started from the United States military in the 1950s. They were looking at the combined environments you might see in certain vehicles, like a jet aircraft, for example, and trying to simulate those environments to increase their overall component reliability or product reliability. So the test parameters themselves are going to be based upon your end-use environment. So if you had a product that could be subjected to something like this, you need to think about the environment. For our laptop, maybe it could be used in an aircraft or in a extreme off-road vehicle. Who knows? Something like that, where you get temperature and vibration extremes. So some commonalities, though, typically we'll have the unit turning on and off cyclically to stress its internal components and making sure it's still functional. The temperatures will vary by application. For the fighter aircraft example, and this is described in the Mill Handbook 781 document, they use a cold temp of minus 55 degrees C, so that's going to be high altitude, very cold, and a high temp of 71 degrees C, so sitting on the tarmac cooking. The vibration itself is usually done in a single axis, just for the sake of convenience. They're simpler to test that way. And depending on the application, that might be where the primary excitation energy exists. It is possible to test 3 axes simultaneously, although that's a much more complicated and expensive thing to do. The vibration input itself is random vibration, so you're simulating multiple frequency inputs at the same time. For transport applications, this is generally lower frequencies, so 1 to 300 hertz, especially when packaged. For bare product frequency, though, looking at, you have higher frequency vibration content, so often you test between 5 hertz to 2 kilohertz, and again, this is all going to vary by your application and environment. 2 standards that discuss this are MIL 883 and MIL 781, but oftentimes these are specified, custom per the application. Common issues and results, as you may expect, would be unsupported and surface mount component failures, so things falling off PCB boards, especially large caps, inductors, that sort of thing. And then also, as MIL Handbook 781 defines it, the permanent failure to operate correctly. So basically the unit failing to work for some reason or another. For many applications, you may be able to find these failure modes with just temperature or just vibration, but it's not too hard to see how things would act differently if you're at a very high or low temperature. Herb, would you like to add to this?
Thanks, Mike. This whole area of agree testing was part of a huge effort by the military that started in the 50s, as Mike said, and it was interesting when you see the progression of it from 40 or 50 years later. Basically, you had a lot of hardware that came out of World War II and the beginning of the Cold War, things like that. The sophistication of the hardware increased many-fold, but the reliability didn't. So I've heard war stories, and you probably have as well, of things like ballistic missile submarines coming back into port with a live bird in the tube because the darn thing didn't work when they told it to go in a test. And lots of things like that. Well, the military just absolutely jumped through hoops. Some of you have heard the term, the name Hyman Rickover. He was basically the father of the nuclear navy, and boy, he was just one of the ones that just jumped up and down and beat on the desk in order to improve the reliability of military hardware. One of the things that came out, one number of things came out of that. They sent military people to school, and they created the Naval Postgraduate School and the Naval War College, and they sent a lot of people back for master's degrees. They also, that's when the big mil-spec boom hit the market. They just absolutely came on with these mil-spec, and they're all was intended to improve the reliability. Out of that came this so-called advisory group on reliability of electronic equipment, which is AGREE, as Mike mentioned, and it really showed its value in that in the early 60s was what really starts. The build-up for Vietnam was going on at the time, and a lot of this stuff was a lot of hardware that they were testing was required to pass these tests, especially AGREE tests for the first time. So there was a lot of moving and shaking, literally and figuratively at the time, but it has proved its worth over the years, and it's one of the first and still most highly used combined environment tests. So, Mike, you want to tell us a little bit more about the impact testing?
All right, thank you. So our next one is going to be impact testing at extreme temperatures. And again, for here, impact, we're referring to mechanical impact striking your equipment under test. So background to this, if you can imagine just about anything from a stray baseball or dropping an object, like a tape measure onto your, again, rugged laptop, any number of things can cause a mechanical impact. So the point of the testing is primarily a safety concern to make sure if this happens, you're not going to have a big mechanical or electrical hazard with your product. Typically, this is done at room temperature, but as we can all easily envision, at extreme temperatures, mainly cold, you may have different or unique failure modes. So typically, there's two ways to do this. Either you'll condition the EUT to the cold temperature, quickly remove it from a temperature chamber and test it, or occasionally you'll test at the extreme temperatures. And this is preferential, but kind of hard to do. So what we have pictured here is a hail impact system. You can see that on the top picture, and it's going through a chamber port into an environmental chamber where the laptop is, and that could be at very cold, low temperature. So all of the polymer components would be much more brittle. So if this laptop could be used in a very cold environment, and maybe you're doing it storm chasing or something, who knows, this would be an applicable test for you to follow. There's two general approaches to the impact itself. Steel ball is a common source to impact a general impact, so it's unlikely a steel ball bearing is going to drop on your product, but it simulates well kind of any general impact. Variables there are the ball diameter, which are generally 1 to 2 inches in diameter, and a drop height. Typical is about 51 inches with a 2-inch steel ball, and that all varies on your application and what you're trying to do. The hail impact test is actually simulating a real-world environment. For terrestrial hail, typically it's a 1-inch diameter spherical ice ball going 23 meters per second, which is the terminal velocity of that. There is also ballistic hail to do on aircraft testing, and that's a whole different animal. Test standards are listed here describing some general impact testing. The common issues and results are mechanical or cosmetic damage. Often these tests are thought of more as a safety test, so you may expect damage or somewhat catastrophic damage, but it's critical that the product is still safe. It doesn't pose a large mechanical or electrical hazard. Herb?
I like to call this test the catcher test. Baseball, the catcher is the guy that gets all the balls thrown at him. As a young kid, I was a very much undersized catcher, and I can remember catching a ball in the chest at very cold temperature, and I almost died. I swear, it was terrible. It wasn't unusual to catch one in the chest, but it was a little warmer. I somehow had the ability to absorb it. It didn't take as long to recover from it. Put it that way. So, impact testing like this at temperature extremes is a concept that's been around a long time, not just for catchers, but for product reliability as well. And certain products, just like me, have very different characteristics in cold versus hot environments. Extreme cold tends to cause a brittle-natured failure, as Mike mentioned, in thermoplastics and similar materials. Hot environments can cause a large increase in the level of plasticity, maybe even in me, I'm not sure, especially with oleofoams and cross-linked polymers. So temperature extremes and impacts is something that's been around for a long time and something that, as I mentioned, I can relate to. Mike, how about drop testing?
All right, thank you, Herb. So next we're going to talk about freefall drop testing. So this is dropping your laptop or your cell phone or what have you, hopefully by accident from waist or higher drop height. Sometimes this is called impact testing, but for the sake of our conversation, we call it freefall drop testing. So typically this is done just for sake of convenience at room temperature. However, with most plastic parts, plastic housings, and also glass actually as well, things become more brittle with colder temperature, and also things become very soft with highly elevated temperature. So with all these things, you need to start by defining your environment and considering what extreme environments your product may be exposed to. In general, cold is more severe than warm for this type of testing, but not always. And in general, we use a waist height drop for most handheld products, so usually 1 meter is used as the drop height. Although we see 1.5 and 2 meters pretty commonly depending on the product. The test parameters, typically you'll precondition the samples at either minus 40 C or minus 20 C, and then on the warm side, plus 60 or C or so is pretty common. Just the way the testing works, generally we have to precondition the samples, very quickly remove them from the chamber, and immediately subject them to the product drop. Some variables are the number of drops, or number of drops per sample. For severity, it's good to do every face, edge, and corner, or at least a subset of those. And then also to specify the height, as I previously discussed, and the impact surface. The most severe are generally very hard, so steel plate or concrete or something similar. However, they may be overly severe for your application, so things like a wood floor or a carpet sample or laminate tile floor generally are a little bit less severe, and it's all going to depend on your sample. The height and impact surface are also going to depend on the weight. The heavier the product, generally the lower the drop. So you're unlikely to drop something very, very heavy from that great of a drop height, whereas something very light, like a cell phone, you might drop from, near your head, so maybe a higher drop height is applicable. Test standards here, the ones listed anyway, do discuss product drop, not so much temperature extremes. Those are often done, again, based upon the requirements of your product. Common issues and results are cracking, breakage, cosmetic damage, other things you would expect from product drop. Again, to reiterate, you may find unique failure modes with this that you wouldn't see with room temperature drop testing, and that's the reason why it is done. Herb?
Thanks, Mike. The testing terminology, as you mentioned, tends to cause problems in this particular area because the word impact can mean a number of different things. Previously, we talked about the impact testing plus temperature to mean the product itself is impacted with a rigid surface such as a steel ball, or what I call the catcher test. The reality of a product in use means that the product itself can also be dropped or impacted against a rigid surface. To avoid confusion between the two, that's why we decided to call this the drop test. Product drop testing at temperature extremes is a concept that's also been around for a long time because, as Mike mentioned, polymers get, for example, and most materials get brittle when they're cold and tend to be less, a little more elastic when they're warm. And then the differences between materials rigidly attached together at temperature extremes can also add to this, especially with differential thermal expansion. So this is what we refer to again as free-fall drop testing at temperature extremes, and it should be differentiated or at least thought of differently than impact testing, which is basically what I call the catcher test, or some rigid body impacting the unit that you're talking about. Next item that we're going to cover is mechanical cycling. So Mike, take it away.
All right, thank you. So the next one, this is a personal favorite, for whatever that's worth, is mechanical cycling at temperature extremes. So mechanical cycling, we're talking about hinges, switches, buttons, connector insertion removal. So on our laptop, that might be the power cord or USB cord, that sort of thing. And also touchscreens. So on a laptop, that could be the trackpad. Maybe it has a touchscreen display, anything like that. Basically, you want to life cycle test these. So if the certain key might be struck 1,000,000 times in its life, or that's what you model it to be, it's a good idea to test it to that and make sure that it'll actually survive that level of test input. So typically, you define the number of cycles, the cycle force, speed, and duration, and then also either testing periodically or having the unit functional and being able to log the inputs and note when a failure occurs. So that's all done at room temperature very commonly, but it's also a good idea to combine this with extreme operating temperatures. So with our laptop, it could be used, climbing Mount Everest, it's mighty cold outside, or in a very, very warm day outdoors somewhere in a desert. Will everything act as it should over a long number of cycles in those extreme environments? And this test will allow you to ensure that. So what we have pictured is a laptop in a small temperature humidity chamber. We have a single actuator set up to push the space bar, and you can see that on the bottom two pictures. This is just a demonstration, though. We could, with some machining, put an actuator over every key and button on the laptop and test them all in sequence or simultaneously as appropriate. The test standards for these vary a lot. This is one area of testing where just about everything is defined by the customer for reliability purposes, not so much as a standard or requirement from an industry standard. Common issues and results would be faster than expected wear out, things breaking, types of inelastic deformation. So very cold things might be brittle and snap, or very warm things may soften and not recover. You may have change in actuation or insertion removal force. So a concept here is called the click ratio or snap ratio. And the idea there is there's some mechanical ratios, if you would, of the amount of force required when you press a button to get a good tactile feedback. You want a relatively high amount of force to push the button down and then have that force requirement drop about the time the button actually actuates. And those relative ratios from one to the other, the force to deflection characteristic, is very, very important. So if that changes as a function of product temperature or changes as a result of many product cycles pressing the button a bunch of times, that's not good. And the good news, though, is you can characterize that and test to that. And lastly, just in general, exceeding material limits. So going over or under temperature may cause mechanical failures. Herb, do you want to add to this?
Thanks, Mike. This mechanical cycling can include not only the actuation of button and knobs, but also the insertion and removal of styluses, the rotation of upper and lower body sections of a product, and a variety of other combinations in addition to what we call button cycling. When these events involve any kind of friction between two surfaces, the temperature of the surface can greatly affect the test results. For example, cycling of surfaces with friction damping at high temperatures can greatly increase the smoothing of the surfaces, resulting in a lack of friction at lower temperatures. So at times, this effect has been known to decrease the intended damping of a rotating member, for example, resulting in product damage. Sometimes we've actually seen hinges get to be tight at higher temperatures, and sometimes hinges that were designed to hold at a certain position with internal damping at low temperatures because of the contraction of the material would actually fall out. So make sure you test all these mechanical devices at temperature extremes. Back to you, Mike.
Thank you, Herb. Just in general, if anyone has any questions throughout, please ask them and we'll try to answer them as we go. The next one up is temperature and pressure combined. So pressure could be altitude, a very low pressure, or it could be high pressure or submersion or depth. So the terms altitude, pressure, vacuum are all used somewhat interchangeably, so you have to be careful you're calling things correctly. The units here get sometimes confusing. So often we think in PSI, so the pressure here is about 14.7 PSI at sea level. We may think about torr or millibar or atmosphere. There's a large variance in this. There's not like one industry standard or norm. Kilopascals are another common one. So with this, it's very important to define in your test plan, and when you're reading test standards, are you talking about absolute pressure or gauge pressure? So absolute pressure, right now, where we are, it's 14.7 psi, but the gauge pressure would be 0 psi, because gauge would refer to difference over atmosphere. So make sure those are defined. Obviously, if they are confused or mixed up, you can have an unintended, either overly severe or overly mild test. Next is to define our environment. So think about shipment and end use. Shipment, luckily, is very well characterized. Things are generally tested to a 14,000 foot elevation equivalent. As a note, most cargo aircraft is now pressurized to around 8,000 feet or lower. So in many cases, the motor transit is more severe, going over the Rocky Mountain passes, for example. Those are commonly tested at more or less room temperature, 23 degrees C, sometimes tested at 5 C. But in many cases, a colder temperature may be more appropriate. These are very applicable for anything that has a sealed volume or potted parts where there might be air trapped inside, sealed packages, that kind of thing. It's also good to think about your end-use environment, though. So that might be much more severe, either much higher altitudes, or you may have high pressures. If you could use your product when scuba diving or in other submersive environments, think about all those pressures or low pressures and what those are and try to define them. When doing this, the test itself, generally they're pretty short in duration. We'll do high and low temperature and high and low pressure, so again a four-corner test like we've discussed. It's good practice to cyclically operate the unit, especially at temperature extremes. One result we see often is a reduction in convective cooling capacity of a product. So imagine our laptop. It's in the chamber at high temperature and at low pressure. So you're in the summer in the Rockies, and the laptop uses an internal fan to force air through and cool itself. Well, there's a lot less air for it to cool itself, and that can create operational issues. So that's one of the things we're looking for in this testing. There are many standards describing altitude, not so much the combined temperature and altitude. Again, that's going to be very specific to your product requirements. Common issues and results would be expanded or imploded parts, and the thing I'd say to that, most people think of venting pressure. So if you have a sealed volume, you go up in elevation, you let the pressure out, and then people forget to think about allowing air back in, so when you come back down, the whole thing implodes. I've seen that many times over the years, so something to keep in mind. And also think about the unit overheating if it's operating, especially in warm, high-altitude environments. Herb?
Well, thanks, Mike. The altitude above sea level is, as Mike said, a substantial factor in the density of air, and thus its ability to hold the heat and then to dissipate the heat. The ability of a heat exchanger to properly cool a product can be grossly compromised at altitude. Therefore, any product that is air-cooled should be tested at healthy levels where people actually use the product. Levels often include 7,200 feet for a kind of a normal level. That's where Flagstaff, Arizona is, by the way. And extreme levels going up to as high as the 14,000 feet, as Mike mentioned. Strange, Mike touched on it a little bit, that you actually get higher altitude exposure on trucks than you do on aircraft. All aircraft, commercial, cargo, every aircraft is pressurized to 8,000 feet because they've got pilots flying the darn things, and they don't want to get the bends. And there's only one pressure bulkhead on an aircraft. That's the fuselage. Don't let anybody tell you different. Ask any aircraft pilot, they'll tell you that they're always pressurized at 8,000 feet. But if you ship something over the Rocky Mountains, for example, or other places in the world, you can easily get to levels of 14,000 feet. It's also interesting that variations on this theme include things like vibration plus pressure and temperature. This has become what we consider to be a pseudo-standard for products such as, believe it or not, ice cream. Ice cream is a whole series of closed cells. You ship that to higher altitudes, inside the cell wants to blow up, it wants to expand. And that means the ice cream is going to expand right out of its container. And by George, if you look at ice cream in ski altitude areas, that's what you'll see is blown up ice cream. And it affects the flavor too. So these are some of the more common things that occur, and it's also something that's pretty subtle. It's not right up front like that. So it's something you should definitely test for, considering your test plan. Mike, what's next?
All right, the next one up is fluid submersion with temperature and pressure. And it's important to say here that this does not apply to that many products, but it's a very good example of an extreme combined environment that is very applicable to some products and very important to test. So the idea here is if you have your product and it could be submerged in fluid, either more or less at sea level, like in a pond or puddle, or with depth. So imagine if you're 10 meters underwater scuba diving or something similar, we'll simulate that here. So what we have are pressure pots. We'll put the product in the pressure pots, submerge them with fluid, and then put a head pressure over that using air to simulate the depth. Occasionally we'll also do this with low pressure, but that's less common. If possible, consider operating the AUT, especially if it's going to be operating in this extreme environment. For the test itself, there's two types we do. One is what we'd call a hard freeze test, where we'll use water as the fluid, usually, and go ahead and hard freeze it. So make a big ice block, and if water can enter your product anywhere and expand when it freezes, it will generally create damage. The other extreme test we've done is a non-freezing test. So we'll use a water glycol mix, and we'll go ahead and cycle it between minus 40 or 50 degrees C up to plus 80 or 90 degrees C, and you're doing a huge thermal stress on all of your components while that fluid could be forced into the product, but not actually doing a hard freeze. The test standard we have referenced here is IEC 60529. That is the IP or ingress protection enclosure standard. So if you've ever seen something that says IP 67, something like that, that's where that comes from. And that second numeral describes the fluid protection of the product, and 7 is a submersion test, so we'll do the submersion test using the exact same thing. This is an add-on to it, though, however, combining the temperature input. So for some extreme products, it may be very applicable. The other test standards that discuss this are the NEMA test standards, National Electrical Manufacturers Association. So you might hear the term NEMA 4 or NEMA 6, and that also describes a water resistance pressure rating. Common results and issues would be water entering the product, especially if it's electrical, having electrical operational issues, etc. With the hard freeze, you may have mechanical issues if water is allowed to enter into your product. Herb?
This, on the surface, this seems like a ridiculous test, extreme for most products, but actually it's been shown to be very effective for determining best designs for some products that were supposed to expose to the harsh outdoor environment. I'll give you an example. Any of you who drove to work this morning probably came through a number of stoplights. And guess what? Major components of those stoplight systems have been subjected to this very test, and it's considered a standard for most of them. And those that work consistently probably were subjected to it and passed it. So even though it seems extreme and severe, a lot of this kind of stuff is designed for things that we rely on a daily basis. Okay, Mike.
Thank you.
What's
All right.
next?
Well, our next one is also our last one, and we're going to discuss thermal shock by water spray. So the idea here is to simulate a quick thermal change that may be caused by a sudden water spray. So the scenario to envision here is if you have a product outdoors in a very warm environment, so we'll take the desert, and you have radiant heat energy from the sun, you can see heating of 20, 30, or 35 degrees C above the ambient air temperature. So a very warm day might be 40 or 45 degrees C. We're talking 110 F. And you may have a 30 degrees C temperature rise above that. So you could have a product surface temperature of 70 degrees C or warmer. And there are tests, as an aside, to define all that. If the sprinklers come on or there's a sudden thunderstorm or something like that, the unit could be exposed to cool water, and generally the water temp will be somewhere around 15 to 20 degrees C, and you'll very rapidly cool the product. It's truly a thermal shock. This is discussed in the IEC 60529 standard. It was just revised, and they added a test somewhat covering this. Again, not applicable to many products, but very applicable to some products. As you would expect, common issues and results would be water getting into the product, and that's probably just a function of the water spray, but you can see implosion of parts due to rapid cooling and not having sufficient venting, or things like cracking or other failures, and that's in general due to the thermal shock. Herb?
The heat density of water makes this a very convenient medium for quickly changing temperature of a product and other components. There was a really neat landmark study done in 1955, just recently declassified. It was done by the Jet Propulsion Laboratory, and it showed the potential for disastrous cracking of impeller blades when a jet turbine engine is subjected to a water spray. It was originally intended to increase the power of the jet engine by inducing some fluid into the compressor section. They found out that the turbine blades didn't like that a bit. The study actually goes on to show how they actually resolved the issue, but the fact that the density of water makes it a very, very convenient thing for this thermal shock testing, and it's used in ways that might surprise many of you. So keep it in mind. It's one of the ones that's in our combined environments testing quiver, if you will, and it may be very important to you in the future. So, Mike, you want to wrap this up?
Thank you, Herb. I understand we have a couple questions. We'll just go over our kind of summary and parting thoughts of what we'll discuss, and then we'll get into your questions in just a minute. So some kind of summary points here. First, define the environment and establish your acceptance criteria. It's unlikely any product would be subjected to all 7 of these test inputs, and if you have that, you have one heck of a product. But there are probably these and perhaps other combined environments that may be unique to your product, and that's the point of all this. Before you get into actually testing these, though, test all the single environmental inputs first, and address those failure modes, it would be very unfortunate if you started with combined environment testing and identified a failure mode and couldn't find the primary driver of that. So after the singles, test the combined environments. Expect to have findings. Despite the best engineering and planning, oftentimes there are findings and opportunities for improvement, and many times they aren't the failures that are anticipated. There are other things that failure or come up that aren't the things that are foreseen. And lastly, don't forget about shipping your product, especially for larger capital goods, so things like 19-inch server racks or big capital communications or medical equipment. Shipping is often the most severe environment the product will see, especially the installation portion. So when you get to the end point, you uncrate, you install, that's where you can see problems. Herb, you want to add any thoughts?
Thanks, Mike. I'll wrap up very briefly, too. It's important to re-emphasize, really, that the results of reliability testing are hard to predict ahead of time. And as Mike mentioned, you should expect the unexpected, and especially expect failures. Look at it this way. How in the world are you going to answer the old manager who says, hey, you have an over-designed product there, unless you've actually been able to take it to the failure level and say, nope, I've got exactly this amount of margin built into it. I know exactly what it'll take, and it's not over-designed. I don't have too much money into it, but it'll pass what I need it to pass, and it's going to be very reliable. So that's really one of the really benefits, I think, of the so-called margin version of the testing rather than just testing to spec. And then finally, as Mike mentioned, must be emphasized that for almost all products, the shipping environment represents the most severe mechanical hazards of the product's entire life cycle. So don't forget it. And let's face it, a good product at the end of your shipping dock doesn't do you any good at all. You only get paid, even the janitor, even the CEO, no one gets paid until the customer has the product and has a big smile on their face. Then you've done your job. And that's why we do this reliability testing, and that's one of the reasons that we emphasize don't ignore the shipping environment. It's a severe component. Everyone's got to do it. It's got to be shipped. Unless your client's next door, you got to ship your product, and oftentimes nowadays that client's half a world away. So don't ignore shipping. So with that as a final parting shot, pardon the term, we'll ask for questions. Greg?
Great. Kind of along those same lines, Herb, we got a question here. If people in your company object to testing for weakness, how do you justify to management that you actually need to run the testing?
Well, the liability is probably the biggest reason you need to run the testing. You really have to know the safety and the suitability of the product. So I don't think that there's much argument about running the testing at all. Testing to margin that might be a question, especially if the products are very expensive, and I can fully understand that. So it's a cost trade-off type of thing, and for each product it's going to be different. Surprisingly, of the number of damage boundary tests, for example, that I've run over the years, only a half a dozen or so have been utilized the right number of products, 12 full products, simply because they were too expensive. So you can get a whole lot of information by doing testing to level and seeing where the failures are, and then being somewhat conservative about the approach that you take in either in shipping or in the design or product buildup or product changes, things like that. Almost always you get very valuable information. Hard to predict ahead of time, but very valuable information about the product characteristics, what's likely to occur, and what's the liability for that event. Mike, do you have anything to add to that?
Just briefly, I would say that when you do this type of testing, hopefully you can get as much value as possible out of the test. So when you do something, just even a temperature test, you might be looking at your materials, you might be looking at your manufacturing processes, your assembly. There's a lot of value to a lot of different stakeholders with these tests. And then from a business perspective, like Herb mentioned, the long-term liability and warranty costs of having a defective product and having to do, at best case, a recall, or warranty claims, that's really expensive and could be potentially bad. So by doing all this product reliability testing, you're less likely to have one of those events occur, which is really a good business practice. So hopefully that helps justify the expense. Good.
Okay.
Greg?
Great. Thanks, guys. Next question is, This person asks, I would hope that the product would at least be tested to the product spec level, even in the expected combined scenarios. To demonstrate even more product reliability, wouldn't you test beyond the product spec? And they also question about halt and testing to failure.
Okay, so that's a lot of question. In short, many products have some basic product safety tests they have to pass, and those are generally very minimal in their reliability component. They're most looking at safety and what happens if you have a high voltage surge, that sort of thing. It all depends on the product. The test to level versus test to margin question is an excellent one. It's a good idea to define the anticipated number of cycles or extreme environments your product may be subjected to, and to verify it can be subjected to all those environments and survive. It's also a very good idea, though, to go beyond that and to see where your product fails. So let's say your product can be operated in environments up to 60 degrees C, and it does that. Awesome. Can it go up to 70 degrees C? And if so, that's very good. You'd hate to have it fail at 61 degrees C and not have that much margin. Another example would be the space bar will be struck 1,000,000 times. Excellent. You wouldn't want it to fail, though, at 1,000,001. If it does 1.5 million, 2 million, you have a good amount of margin there, and that's a very good thing. Herb, do you want to take the halt portion of this?
I'd love to. HALT is something we didn't mention during the presentation, but it stands for Highly Accelerated Reliability Testing, or life testing rather. They don't refer to it as test at all. They actually refer to it as a screening or as a stimulation or a stress or something like that. It consists of thermal extremes, and those who run it will tell us that the thermal extremes wind up flushing out maybe 80% of the failures that they find. The vibration portion of HALT comes from the product mounted on a floating plate within a chamber, within a temperature chamber, and this floating plate is then impacted with impactors, hammers, under the plate, such that if you put a transducer on the plate, you would get input in 6 different orientations, X, Y, Z, roll, pitch, and yaw. Doesn't mean those are controllable, doesn't mean that they are shaped, it just means that you have input. So you can increase the noise level, I'm going to call it, which is really what it is, by simply cranking up the amplitude, putting more pressure, air pressure behind these air hammers. It doesn't necessarily produce a controlled environment input as far as vibration is concerned, certainly not to the extent that an agree test would do it, either in single axis or multi-axis. You can measure the overall GRMS of the vibration in a HALT test, and you can get 40 or 50 GRMS. That's not unusual. You put that same product on a electrodynamic shaker and give it the same input level, it'll fail at half the level normally. So there's not a good relationship between the call out of vibration in a HALT test and a real agree type temperature and vibration test. So they're 2 very different things. Unfortunately, they look the same. They're often sold as the same thing, but they're very, very different. A horse of 2 different colors. I'd love to talk about that. Maybe that's a subject for another webinar, but that's about all we can do in a couple of minutes. Greg?
Thanks, guys. That's all the questions we have right now. So I'm going to throw it back to Mike here for a little bit more wrap-up.
Awesome. Thank you, Greg. Just really quick about Westpak. As you may or may not be familiar with us, we are a contract test and measurement company. We have 2 laboratories in San Jose and San Diego, California. We run an ISO 9001 quality system that covers our basic QMS requirements, and we also have an ISO 17025 laboratory accreditation, so that covers most of the testing we do and calibration of our equipment. Our assessing body is A2LA. We also do other things that we didn't discuss today. So we do all the obviously combined and single environment reliability tests. We also do a lot of transport packaging testing. So for both single parcels, crates and pallets, that sort of thing, we do all that packaging testing. We do dangerous goods packaging certification or DOT testing. So if you're shipping something hazardous like an explosive or a bioagent, what have you, we can certify that packaging. And we also do a lot of stuff with the medical device industry, testing sterile barrier, medical device packaging, that sort of thing. We have a lot of different test capability. There's a lot of overlap from industry to industry, and we also do a lot of work doing what we discussed today, specialized one-off type tests. Next thing to talk about, our next webinar will be May 15th in about a month. The topic is life science medical device packaging, and we'll be going over some of the industry test specifications and some updates to those that have been made recently in the implications of those. That is it for us. Herb has a couple things to mention, and then Greg will wrap it up. Thank you.
This webinar will be posted on our website probably within 24 hours, and you can listen to the whole darn thing again if you're really bored, or you can just read portions of it because both the printed and the actual audio version will be there. And any feedback that you have would be highly welcome. We're trying to make these the best possible medium by getting information out to our relevant public as possible. So any feedback that would help us do that would be more than welcomed, and so thank you very much.
Great, guys. Thanks for the webinar. If you, like Herb said, if you missed anything, it'll be posted to our website at www.westpak.com, and please check out our new website. It launched today, and it's got a lot of new great tools on there and a kind of a cool layout, so let us know what you think about that. I just got the PDF will be uploaded on Monday, and the video will be there by Tuesday for download if you want to view the video. If there are any webinars you'd like to see, please email us at webinar@westpak.com. That email at the bottom of the screen there on the last slide. We will be sending out a survey following the webinar. Please fill it out because we are always looking to improve our process. And if you have any other questions, like Herb said, please email them into webinar@westpak.com. Thank you all for attending. I'm Greg Schwinghammer. Make it a great day.